Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We're very happy to have Zev Dvir here today. Zev graduated from the Weizmann a few years back. Yuval, would you like to have a seat? Part of my introduction. Zev, of course, worked extensively on various aspects of algebraic computing, and today he'll be telling us about rank bounds for design matrices with applications, with or without a comma.
This is better, right? The lighting wise.
The lighting goes down.
Okay.
So all kinds of magical things will happen during the talk.
This is just one of the...
No, I did it.
Oh, you did?
Yeah, there's a control panel here.
Wow.
Okay, so
We might have to invite you again to do it in the next talk.
It says lights. Okay. Thank you for inviting me. So I'll talk about this very recent joint work with Boaz Barak, Wigderson, and Amir Yehudayoff. And so it's as you can see, it's a very long title. We're debating whether to put a comma here or not. If you have if you think it's wrong, then I would be happy to know it, because we had what?
Far worse problem.
If you can think of a better title, shorter, better title, I'd be happy to know. Okay, so the talk will be about mostly about matrices, and mostly about complex matrices. So this is an example of a complex matrix. And when you say a matrix, the first thing you think about is the rank. What's the rank of this matrix? That's usually a very interesting property. It's very useful in many situations. That's an algebraic property. Another thing you might think about is the support, or if it's the places where it's zero or non-zero. It's like it's more of a combinatorial property. So you can look at the matrix and say, it's a tridiagonal matrix, or it's a sparse matrix, and so on. So you can look at the structural properties of the matrix, and the topic of this talk is kind of the interaction between these two properties. And as I hope I'll convince you that once you can prove some connections between combinatorial and algebraic properties, then these things can be very useful and very powerful. Okay, so this is kind of the very high-level overview. And this type of questions come up in many different ways in many different areas. So a very non-exhaustive list is, first of all, coding theory. There are many families of codes that are locally decodable, low-density parity check codes, and so on, that are defined by the dual. So you have some sparse matrix, a matrix with sparse vectors, which are the constraints on the code, and finding these matrices with some combinatorial properties and low rank gives you good codes with very nice properties. And we'll see examples later. Another place is in computational complexity, where problems, very natural questions in circuit lower bounds and communication complexity and other areas translate to questions about rank of some structured matrices. Also, in mathematics, there are questions in graph theory where you look at the adjacency matrix of the graph and you try to minimize the rank of a matrix with some structure. Questions in combinatorial geometry that I'll get to later, matrix theory. And even in practice, there are questions that are of this form, like low-rank matrix completion, when you have some partial information of a matrix and you're trying to extend it to a low-rank matrix. So there's, again, structure and rank and so on. So it's really interesting, a lot of interesting questions. The underlying question is kind of to understand the minimal rank of a matrix that has satisfying some structural condition. The minimal rank or the maximal rank. Okay, so the main theorem is the following. We show that, So informally, we show that if the support of a matrix satisfies some property which we call a design property, then it has very high rank. So it's a very large class of matrices for which we give a rank bound that's not very clear a priori. And this is for complex matrices and also for any field of characteristic 0. And we get two applications from this theorem. One is about line point incidences. So these are some questions in combinatorial geometry where we can we generalize kind of old theorems of Sylvester-Gallai and Motzkin-Rabin about incidences of lines and points in space. So I'll talk about this later. And we also get applications for a more computer science question about locally correctable codes. And we show that...
Complex.
What?
But over the complex.
Yes. Yeah. Everything is over complex.
Which is not the standard.
Yeah. So these questions, I'll talk about later what the motivation for these codes and why we're interested in them. But yeah, so we show that these codes cannot exist over complex numbers as opposed to finite fields where they do exist. So
sorry, when you say support of a matrix, you just mean the span of the column?
no, the support is just the places where it's non-zero.
All the entries sparse.
It's like
This is
the
zero
Oh,
non-zero
okay,
property.
okay.
it's like the graph of the if you look at the places where it's not non-zero, and this gives you let's say a 0-1 matrix,
Right.
kind of. Then it's like a graph. The places where it's non-zero, that's the support. It's a subset of the yeah.
By the way, I mean, in practice, and when you think about these kinds of questions over the complexes, the more reasonable question would be, what if I tell you that most entries are very, very close to 0, so 10 to the minus 6, and other entries are significantly great, so greater than magnitude, complex numbers of magnitude at least 1.
So these questions are kind of tend to be easier, I think, if you think about L2 kind of L2 norm, but
And can you extend your thing to looking at this more generalized notion of
well,
support?
if you
I mean, rank is not a smooth word.
yeah. Well, if you bound the non-zero entries by kind of reasonably not too large and not too close to 0, then these questions become easier. That's what I was kind of trying to say. What makes these questions hard is that you don't bound the entries.
So when it's non-zero, you're saying?
Yeah, but if you're only close, then I'll have to
Maybe
have
even
to think
easier
about
to
it.
I
rank
think
up.
that maybe motivation for phrasing this way is that sparse matrices you can just present in a more succinct way, and if you have all kinds of weird things like what you said, then it becomes a problem to represent.
You can approximately represent them.
Yeah.
That's
Which is what he does.
Yeah. So for the theorem that we prove, actually, I mean, if it's just close to 0, then I don't see how to prove them. It's a good question. Just for the applications, you get the 0. So yeah.
So does complex numbers here in the theorem, or
What?
so where is it important that you deal with complex numbers, or is it
Where is it important? In the proof.
I mean, the statement makes also sense just over the reals, or
Oh, the reals. Yeah, when I say complex, just to make it as general as possible, it's also over
I
the
see.
reals. It's in particular, it's true over the reals. It's true over the complex numbers, because the rank is.
So what about big finite fields?
Yeah, if the characteristic is sufficiently large, I'll get to this later. It's very large characteristic is basically the same as complex numbers. So yeah. Okay, so so I'll start by just talking about the main theorem and the proof, and then I'll go to the two applications and talk about them. But first, let's just see the theorem and the proof, which is not very complicated. So I want to define this property, this design property, formally. So an m by n matrix, m will always be bigger than n, so have more rows than columns. So we call it a QKT design matrix if it has the following properties. So each row has at most q non-zeros. So each row is q sparse. Each column has at least k non-zeros. So there's at least k non-zeros in every column. And if you look at the supports of two columns, they intersect in at most t rows. So if I take two columns, the places where there are non-zeros can be the same in at most t rows. So it's if you're used to hearing about combinatorial designs, then this is a more relaxed definition. In combinatorial designs, usually you have an equality in these all three places, and this is a more general definition.
That are sparse.
Yeah.
So this is some coding problem, right?
Yeah, you can think about this as. I'll talk later about the connection between design matrices and locally correctable codes. It's a very related notion. Okay. So is the definition clear? Okay. So
it's clear in this previous example. Sorry, can you just back up a bit? So to get a sense of this Q condition, is it very trivial or not? If I just relaxed it.
So there's some connection between all the parameters. So you can, but this is the simplest kind of way to phrase it, and it's easy to define, and it's what we need in the application. So obviously, if you think about it, there's some connection between at least on average. I mean, you can give some bounds on average.
Just designs are usually sets and points, and two sets don't intersect too much. But here, it's like maybe the easiest thing is to think about
the sets are the
and
sets of non-zeros.
Too many sets.
But then,
in addition to the usual.
But then there are very few sets and very.
Well, if you think about sets of size q, then you have that two different points don't belong to. 2 points don't belong to too many sets.
Yeah, it's a dual of points.
It's just turn the matrix. It's a known notion, but here we relax it to inequalities to make it more general. Okay, so here's an example. You have three non-zero in every row, at least 5 non-zeros in every column, and the intersections. If you check, the intersections of every 2 columns is only in 2 places. Okay, so a priori, if I give you this matrix and I ask you the rank, other than computing it, you can't really, there's no easy way to see what the rank is. But once you figure it's a design matrix, you'll know that it has high rank. So this is and the equation that we get, the rank bound, is the following. So any complex QKT design matrix satisfies the rank is at least n minus this thing. Notice that n is the maximum rank you can have because it's the number of columns. And so this is kind of how much you lose in the rank. So it has all the 3 parameters in the places you expect. And this is you see in the application, this expression can be very, very small. It can be a constant, for example. Is it tight? That's a good. It could be negative? No.
It's n squared.
It's squared.
No, but the n minus that thing.
Oh, if it's negative, then it's not very interesting.
Yeah, but it's probably not tight, right? This is what it's.
Yeah, it's not. It's not.
This expression is not what it's supposed to be.
So can this prove that the identity matrix has full rank?
That is, identity matrix says 1, 1, 0. So this is 0. Yeah.
We made progress.
Well, you see later that it cannot be improved. So this square is. I would guess this square could be improved, but the expression inside, if you could improve it.
No. All I was saying is that I would expect something linear for this thing not to become. I wouldn't expect this.
You see in the applications that we get really strong bounds for some of the applications, so you cannot improve this too much without contradicting some line point incidence thing. So the applications get really close to what they should be. So maybe the constants here, Q. Okay, so we think Q can be. We can get rid of Q, but other than that, I'm not sure you can improve it by much.
Then it's kind of this seems about right. Also, you can imagine lots of columns having about square root of n entries, and intersections being of size 1.
Yeah, exactly. Yeah, it seems like kind of the right expression except for the q, and maybe, well, the square, I guess, should be there, but the q shouldn't be there. Okay. And once you have this for complex numbers, there's some nice trick that gives you the same thing for every characteristic zero field and finite fields with very large characteristic. It's a Nullstellensatz, Hilbert-Nullstellensatz argument. So this theorem can be phrased as the identity of polynomials, and then with integer coefficients. So a large characteristic means something like 2 to the 2 to the n. Okay. And for small characteristic, it's not true. So if you take Reed-Miller codes, take the dual of Reed-Miller codes, it's going to be a design. So you take the projective space of d dimensions, and each row corresponds to a line. You basically take the geometric designs and you take the equations that are satisfied by low-degree polynomials, and you get a bound that's you get that this is not true for small characteristic, but it has to be characteristic smaller than n. And again, I'll go back to codes and designs later. So I don't know. This Nullstellensatz thing is probably not tight. I mean, it holds for any polynomial equation. This is a very specific one. So probably, I'm guessing that if characteristic is bigger than n, then, I mean, I don't want to guess too much, but one of my recent guesses was false. But I mean, the only constructions we know are kind of come from small characteristics smaller than n. Okay, so let's see the proof. So the proof is, we had a very complicated proof, but eventually we found a way to use some heavy machinery and reduce the proof to something much shorter. So I'll introduce you to this machinery, which hopefully be useful for other things. It's been useful for other things for decades. But so first, let's see the easy case of the theorem. The easy case is, as I mentioned, is when the entries are bounded. So let's just think of all the entries are either 0 or 1. So then what you do is you take the matrix, let's say it's a real matrix, you multiply it by the transposed from the left. So this has the same rank. And what you get here is that if you look at the diagonal entries, then there's just the square of the L2 norms of the columns. Because they're all ones and they have at least k ones, you get k. And the off-diagonal entries are at most t because they are inner products of two vectors that are 0, 1 and intersect in t places. So it's a very simple thing. And then there are kind of a very simple argument for these matrices called diagonal dominant matrices, which gives you the following bound. So it's n minus this expression. So you get the off-diagonal divided by the diagonal and times n squared. And to get this, it's a one-line argument. You take the square of the trace divided by the trace of the square. It's some textbook thing that I'm not going to show. And this is good. This is even, here we don't have the q. So q is only going to come in the reduction from the general case to this case.
If you don't assume that the matrix is symmetric, then it should be.
Oh, this is for symmetric matrices.
Yeah.
Yeah. This is for symmetric matrices.
No,
yes. This is for symmetric. For non-symmetric, you have to either sum it with the transpose or multiply by the transpose, depending on how high the rank is.
Yes. No, sorry, it's positive definite. But this is positive definite, for example. But is it tight? This argument is probably tight for symmetric matrices, right? And not necessarily positive definite.
Why is this positive?
No,
so this matrix that you came up with, the n by n matrix, is positive definite.
No, so I'm not saying about your
example,
but this argument I think should be tight for general symmetric matrices, right?
I'm not sure how tight it is, but it should be tight. Yeah. If I had to guess. Okay, so now the question is, obviously the difficulty is that the entries are not bounded. They can be very large, and you want to somehow argue about it. And the tool that we'll use to reduce it to this easy case is called the metric scaling. So it's kind of a well-known thing that's been used starting from the 60s. It's used in economics even, and from what I read, the World Bank uses it or used to use it to compute exchange rates between different countries and so on. But so it's a really nice thing. It's been used in complexity theory and other places. So the idea is to find the coefficients for the rows and coefficients for the columns, and to just multiply each row by the corresponding row coefficient and each column by the column coefficient. So you're multiplying the ijth entry with ri, cj, aij. And we want this to be positive real numbers. Obviously, we don't want it to be 0 because we don't change the rank and so on. So yeah, we want to keep the same rank and the same support as the original metric. So, and the real thing is some technicality because we'll need to take the square root of them at some point. But so how would this help us? Somehow, hopefully, this will balance out the entries so that we can use the same argument as before. And so we will need two properties. We will need each column. We need to keep that each column has large sum of squares. This will give the diagonal entries. And we want each individual entry to be bounded, say by 1. And this will give the bound of the intersections. Okay? So it's an optimization problem.
So when you say bounded just from above, right? I mean, you're not
yeah,
saying
bounded from above.
It's not far from 0.
No, if it's 0, it's fine. But so you want to maximize the
Bounded absolute value.
bounded in absolute value.
The entries are complex.
Entries are complex. Yeah. We're going to do the scaling actually on the squares of absolute values. So, but
Is it clear that such scaling exists?
it's not clear at all. That's the big question. It looks like it might exist, right? It's you have a lot of things you could play with, and we had so as I said,
number of coefficients and quadratic number of entries. Like.
Yes, it's not a nice optimization problem, but it's okay. So we when we started out, we had some thing based on if you've heard of Forster's proof of sign rank. It's a nice result from communication complexity. So he has some similar optimization going on where he takes a matrix and makes it nice somehow. And then eventually we found these metric scaling theorems, and more precisely we found a way to use them, and so we get a much cleaner, much stronger argument, statement. So let me tell you the theorem that we're using. So this is originally due to Sinkhorn from 64, and the way it's written here is by Ortblum and Schneider. And what you get is the following. Take a real matrix, n by n. Let's say it says non-negative entries. So as I said, we're going to apply this on the squares of absolute values, so that's non-negative. And now we need to assume some conditions, some structural condition on the matrix A. So we want to assume that it doesn't have too many zeros. If a matrix has a lot of zeros, if you think about it, there's no hope of doing this. If, let's say, everything is 0 except for the first row and the first column, then you're not going to be able to solve this problem. So having large submatrices that are 0 is a big problem. So we need to avoid them. And the condition is that every 0 minor of size A times B satisfies A over M plus B over N at most 1. So the fraction of rows plus the fraction of columns is at most 1.
So 0 minor is completely a 0 matrix.
Completely 0 submatrix. You have A rows and A and B columns such that the restriction to these rows and columns is 0. So, for example, if you have a matrix with let's say, a square matrix with a non-zero diagonal, it satisfies this condition. Because if you have, let's say, if you have two-thirds of the rows 0, you can have only 1/3 of the columns 0 without hitting the diagonal. And so if you have this condition, then for every epsilon, there is a scaling with row sums close to 1 plus minus epsilon, and column sums close to m over n plus minus epsilon.
What do you mean by sums? Sums with
It's non-negative. It's non-negative entries, and the scaling is also positive. So everything is positive.
It's not the same as what we had before.
So
No,
why
but-
can't you just converge with this? I mean, for every epsilon, this is true.
Oh yeah. So if you have strict inequality here, then you can get epsilon 0. You don't need the epsilon because you have this inequality. If you think, for example, about this matrix, then you can get this matrix for every epsilon, but you cannot make it actually 0. Yeah. But yeah, in the application, we're going to take epsilon to 0, so you can safely ignore it. But this is the theorem. And so if it's a square matrix, then you get row sums 1 and column sums 1. If it's skewed, then you get the column sums has to be normalized by, they're going to be a bit larger the more the rows you have. Okay, so this sounds very, very good. We would like to use it. It should solve all of our problems. And the only problem is that this condition might not be satisfied by A. And so we have to work a little bit. Okay, and as I said, you can also use this to normalize the sum of squares of rows and sum of squares of columns, or some fourth powers, anything you want. You just apply this on the matrix with.
Are we now in the special case of 0, 1 entries?
No.
And why do we have real?
Because you take we're going to apply this on the squares of absolute values.
Okay.
Because this is what we need to scale. We need to scale the sum of squares of absolute values of the columns, and we need to bound the absolute values of each entry. Okay. So usually applications of this theorem use, I think this is the first application that actually uses it for the squares, so there's something maybe new about it, normalizing the L2 norm. Or no, it's usually used for row sums and column sums, just L1. And here we use it with L2, so didn't encounter it before. Okay, so I'm not going to prove this. This is it's the proof. So synchronous proof, original proof was when there are no zeros at all. So all the entries are positive, and then you just multiply each row. It's a very simple algorithm. You multiply each row so that the row sums are 1. Then you multiply each column so that the column sums are 1, and you repeat, and it converges to what you want. And Altman-Schneider is it's a bit more complicated. It's there's some SDPs there, and there's more work. It needs to be done. And there are also strongly polynomial algorithms to find the scalings if you really want to. But we don't really care about the efficiency of finding these things. Okay.
To satisfy the 0 minor condition?
No, it's going to be, I'm going to show it. I'm going to take every row and repeat it some number of times between 0 and q. Okay, so that's what I said. So to use this theorem, we're going to build an nk by n matrix, B, from the rows of A, such that each row of A is used at most q times, and B satisfies this condition on the 0 minors. And then we're going to scale B and get from it a scaling of A. So first, let's see how we can build this matrix. So it's very simple. For each I, for each column, we take k rows that has non-zero in the ith column. So we take, for I equals 1, we take k rows of A with non-zero in the first column. Then we take another block of k rows with non-zero in the second column, and so on. So we can do this because it's a design, so that we know that there are at least k non-zeros in each column. And each row is used at most q times because each row has at most q non-zeros. And now you get, this is nk by n, and it satisfies the zero minor property because it has a non-zero kind of generalized diagonal.
Yeah. There's k things that you can get the second time around?
I just look at the original matrix. I can use something that I already used before.
Oh, okay.
Yeah, but I'm not going to use a row more than q times. Okay. So I don't really, it's a very simple message. I just take k rows and then take another k rows. I don't care about overlaps between them.
And is that most q times? Because
Each
you're
row
only repeating this k times.
No, each row has q non-zero, so it can appear in only q of these blocks. And in each block, there are no repetitions.
Right.
Yeah, I don't take, in each row I take q distinct rows. K distinct rows. Yeah, and it satisfies this zero minor property because you can reorganize it so that you have n matrices with non-zero diagonals. It's kind of it's easy to check. So now we get a scaling of this matrix, and so again we're doing this for the squares.
Guarantees that every row is used at least once, is it?
No. We can skip some rows. We don't want to use all the rows.
I see.
We don't care to use all the rows. We can not use some.
I see. So
I only care that I don't use
rows. You'll prove a high rank lower bound, and it still implies a high rank.
No, I'm going to get a scaling for the original matrix. The rows that I didn't use here, I'm going to pick the row scaling just to normalize it to B1.
Rank 1 on B, right?
Yes, but it's not a design matrix, so it's a bit of a problem.
But once you have the scaling,
Well, once you have the scale, I mean, this is not a design. At least I don't.
it's the same rank as A, right?
Yeah, the same rank, but to
I mean, now if you have scaling for B,
the easy case uses the fact that you have a design matrix with bounded coefficients. You need to multiply by the transpose and use the fact that the intersections of two columns are small. Intersections of two columns here, I haven't really thought about it, but maybe if you think about it, you can do it also this way. But we're going to get a scaling of A, and then and then it's really a reduction to the easy case. You have a design matrix that's scaled so that everything is bounded. Okay, so I'm doing with time. Not good. Okay, so now when we scale this using the scaling theorem, you get that the sum of squares in each column is the ratio nk over n, so it's k, right? And with this epsilon that I'm ignoring, and each entry is at most 1 in absolute value. This is because the sum of squares of each row is close to 1. So this is a very, very crude bound. Actually, in the real proof we actually use that the sum of squares is 1. So if one entry is big, the other one can't be too big. So there's some. And now from this you get a scaling of A by just so you look at a row of A and it appears in several of these blocks, and then you just take the. So you need to choose which coefficient to use to scale it. And you just take the biggest one. And for the columns, you use the same column coefficients that you used here. And it turns out that because you used each row at most q times, you're going to lose a factor of q in the sum of squares in A. Because the sum of squares here is k, and the sum of squares in A is at most the factor of q. You have to divide this by q because you can repeat everything at most q times. So it's and the entries are still bounded by 1. So this is where q comes in. And as I said, there might be a more clever way to do this and not get q, and this wouldn't be very surprising. Okay, so now we have the scaling of A. Call this
going into the proof of the
scaling.
Of the scaling theorem and no. Okay.
We tried reading it. Okay, now you take the scaling. There's no time, there's deadlines in conference. So you take the scaling and you multiply by the transpose, then you get diagonal entries that are k over q and off-diagonal entries that are t, same as before, and then you get this thing. And to get 2k here, then that's what I said before. You need to argue that the entries are not just bounded by 1, they're bounded in each row by L2 norm 1. Okay. And an open problem, obviously, to get rid of this dependency. Not sure it's possible, but it might be. Okay.
So wait, I see. So the fact that it's diagonally dominant just follows by looking at the conditions that you had on the row sums and on the column sums.
Well, it's just I know that the L2 norm, the sum of squares of each column is k over q. So this gives the diagonal elements, exactly. Right. Each diagonal element is just the sum of squares of the column. And the off-diagonal entries are the inner products of two vectors that have each coordinate is at most 1, and at most t places where they are both non-zero. So it's just t. Yeah. Okay, any more questions before I move on to the application part? Okay, so now let's talk about line point incidences. Okay, so the starting point is the following beautiful theorem of Sylvester-Gallai. So you have m points, v1 to vm, in the real plane, which is here. And suppose that for every pair of points, vi, vj's, there's a third point on the line connecting them. Then the points have to be all on the same line. So this was conjectured by Sylvester in the late 19th century, and it was proven by Malchior in 1940, and it was conjectured again independently by Erdős in 43, and proved again independently by Gallai in 44, 45. And for some reason it's called Sylvester-Gallai. I guess you take the first person and the last person. And yeah. You take the people with the easiest names to pronounce. And anyway, so that's it's a great theorem. There are many really beautiful proofs of this theorem. It's also so this is for the real plane. It's obviously it's also true for the real space of higher dimension. It's just projected to a plane, and so it's basically a question about the plane. Over the complex numbers, it's not true. In the plane, you can have, say, 12 points in the complex plane that have this property, but that's the only examples are in the plane. So if the points are satisfy this property, they have to be in two-dimensional space. That's a bit more difficult to prove, but it's known. And what we prove, which is kind of motivated by these locally correctable codes, is the following. It's a kind of a robust version of this. So this condition is very rigid. So if you move one point, then you ruin everything. It has to be. It involves all points and all pairs of points and so on. What we show is something with a much more robust condition. So I'll give this definition now. It's a definition of an alpha SG configuration, or an alpha Sylvester-Gallai. I wanted to use delta, but there's some bug in PowerPoint that basically if you write delta, it changes into plus minus for some reason. I don't know, it's kind of well documented on the internet. But anyway, so a set of points in this time I'm going to work in complex space because we can, so why not? It's an alpha SG configuration. If for every I, there are at least alpha m values of j, such that the line between vi and vj contains a third point. So for every point vi, if I draw this picture, and so you have all these lines that have only one more point, and then you have the lines that contain two or more points. And this condition is basically saying that these lines contain at least an alpha fraction of the set. Okay, so if alpha is 1, then you get the original condition, Sylvester-Gallai. So now, what can we prove for alpha SG configurations? So can we show that they're all on the same line? Yeah? No. Right, because you can put the points on 1 over alpha lines, alpha fraction on each line, and then you can put these lines in to span a higher dimension. So the dimension can be at least 1 over alpha. And so can you do better than that? And so the answer is maybe, but not more. So we can show that the dimension is at most 1 over alpha squared. I don't know. The square comes from the square in the rank theorem. So
you're talking the dimension of the configuration?
Yeah, dimension is the dimension of the smallest affine space containing them, or just the rank of the vectors.
Is it also clear that, I mean, could you have come up with something stronger saying that they're all contained in 1 over alpha squared lines?
That's not true.
That's not true.
Because you can take a grid of you take a grid of square root m by square root m, then it's going to be alpha SG configuration for, let's say, 1 over 8, something like that. Because if you take any 2 points in this box, they're going to be a third point.
You just need 1 more point, okay.
Yeah, and that's true also for this. I mean, if you take basically 1 over 4. Yeah. So now the number of lines here is square root m. So yeah, so that's not true. And this is true again for complex numbers and for any field of characteristic 0 or finite characteristic, positive characteristic that's double exponential. Because the proof is algebraic, you get this kind of automatically. Previous proofs were very kind of using properties of the real numbers, complex numbers, using areas, volumes, so on. So
the previous theorem that you were describing, you proved it for the complexes.
yeah.
Were you also claiming something of finite fields at that stage?
Finite fields of characteristic
Very high
2 to the
characteristic.
n, something like
I
that.
see. But is there still a notion of scaling and such?
No, there's no notion of scaling, but once you have the theorem, the design rank theorem, we prove in the paper that every theorem of the form some support implies high rank. If it's true over complex numbers, it's true for all these other fields.
Will
Yeah.
you show the trick?
Will I show the trick? Only if you ask. I can show it later if I have time, or if some people want to go, and then show it to people that want to see. So any statement like this is basically an algebraic statement. It can be stated as an identity of polynomials. Okay, so this is the theorem. I just mentioned that when alpha is very close to 1, you could hope to prove that all of them are on the same line, actually, because if alpha is bigger than half, even, and that's true. So it's known that there's some constant bigger than half, something like 4 over 5 or 3 over 7. I don't know, such that this is known. This was originally due to Zemered Trotter, and it's a big conjecture to prove this for any alpha up to half. So this is kind of the unique decoding regime. This is more of a list decoding thing where there's no unique explanation, and you need to find some list of explanations. Okay, so let's see the proof. So the proof is by reduction to the design theorem, design rank. And the idea is that every collinear triple, every triple of points that are on the same line, so if they're on the same line, that they're linearly dependent. So there's some linear dependence between them, which gives basically a linear constraint on the set of points. And we're going to pick a family of triples and take all these constraints and write them in a matrix such that this matrix will be a design matrix. And so let me be more precise. So we have this set of points and lines. We're going to pick a family of triples. And each triple is going to give me a row of the matrix. So each column here is represents a point. And if I have this a collinear triple, then let's say this is one. So this is the first point, the second point, the third point, the fifth point. And these are the coefficients of the linear combination that annihilates them. So 2 times the first point plus 2 times the third point minus 4 times the fifth point is 0. Okay, so I take all these. I'm going to pick some family of triples in a very specific way and write down all of these constraints so that this is going to be a design matrix. And I'm going to show that its rank is very large. It's going to be like m minus 1 over alpha squared. And this will imply that the rank of the set of points is at most the co-rank of the matrix. So, because this is the matrix this is the dual matrix. If it has high rank, then the points have to have low rank. Okay. So this lemma basically gives the idea. So there is a family of collinear triples such that each point is in roughly alpha m triples, and each pair of points is in at most 2 triples together. So this is basically the design property, because the number of triples for a point is just the number of non-zeros in a column. And the intersections between 2 columns is the number of triples containing the 2 points.
And your Q is 3.
Q is 3 by definition. Yeah. So how do you do this? So you can just go, I mean, the naive way doesn't work. If you just take the previous picture, this picture, and you go for each I and you look at this set and you pick some family of alpha m triples containing vi in these points. This is not going to work because you can have, let's say if you have many points on this line, then it might be, if you're not careful, you might, for 2 of them, they might appear in a triple with this one, with this one, with this one, and so on. So it's not a very clever way to do that. So you need to do something a bit more interesting. Not very, but you basically go over each line. And for each line, you pick a family of triples, such that if the line has r points, you pick a family of triples such that each point on the line is in r triples, and each pair is in at most 2 triples together. Then you just take the union of over all lines of these triples. And this is enough to get this design. So I'm not going to explain much more, but and this structure is not
more than 1 triple from the same line, but if you do, you should make sure that
I'm going
the
to pick
triples don't share 2 points together.
Well, I'm going to pick for a line with r points. I'm going to pick r squared triples, such that each point is in r triples and each pair is in 2.
Is in 2. Okay.
Yeah, there's a way to do it. Use some Latin squares or something. It's something that's known. And that's all. And now you get a 3 alpha m2 design, and you plug it into the theorem, and you get this expression is just 1 over alpha, and that's it.
What will the number of rows corresponding to in this matrix?
The number of rows is going to be something like m squared, but it's not. It doesn't come in anywhere. I mean, it's not.
But the row corresponds to what? It's
a triple.
It's a triple.
Collinear triple. Okay, so that's so the proof is it's a kind of a very algebraic proof. Doesn't use any properties of the field. It's true for the p-adics.
If you just used alpha equal to 1, do you?
Oh, so for alpha equal to 1, we really wanted to get the original theorem. It's for complex numbers, you want to get 2, right? This is the. So we don't get 2, we get 9. And we worked really hard to get this 9. But because this is true for also for other fields, I mean, you don't really know what I don't think anybody looked at these questions for p-adics or something else. I mean, there might be examples of dimension, I don't know, 5 or 6. So But because it's a square, we can never get better than 9 because the thing inside is also always going to be 3. So it's a conceptual barrier to yeah. Okay. Yeah, but the constants are not very big, so that's nice at least. Okay, so shall I go for like 10 minutes? Or okay, so kind of go quickly over the locally correctable codes thing. So first, let me tell you what's a locally correctable code. So I'm assuming you know what an error correcting code is, because I don't have time. But so it's a function that takes a message y into an encoding x, which is c of y, where c is the code. So it's a code over some field. In this case, it's going to be complex numbers, but usually people look at finite fields in coding theory. And now you have some noisy channel which takes this encoding and corrupts some alpha m fraction of the entries. And you want to decode the message, or even better, you want to decode the codeword. But in this case, you want to decode it using only a small number of queries to the corrupted word. So basically, you have a decoder that gets an index in the codeword. And it tosses some coins, and it picks q positions to read. Think of q as 2. And using only these 2 queries, it has to output the value here, the correct value, with high probability. So it seems like a very difficult thing. And so I'm going to define, to be consistent with other things that I'm not going to show you, I'm going to define the dimension of the code to be n, which is the length of the message. So this is kind of how much entropy you have in the code. And as an example of a code like this is, let's say over G of 2, you take the encoding of a message y to be all the linear functions applied to y. So there are 2 to the n linear functions. So it's a code taking n bits to 2 to the n bits. And now how do you decode a position here? So each position is basically an inner product of y with some vector a. So to decode it, you pick a random vector b, and you query 2 positions, yb and yb plus a. And storing them together will give you y inner product with a, and this will be correct with probability, some constant probability if alpha is small enough. So it's a constant number of errors. So it's a 2-query code with an exponential encoding length, or if you think about it, it's a logarithmic dimension. So it's called the Hadamard code, and so it has a logarithmic dimension. And the question you can ask is whether you can do the same thing over the reals or complex numbers. So it's a legitimate question. I don't know if it was asked before, but it's definitely legitimate because we can answer it. So I think I don't know. Dana, you had this thing with Subash where you have locally to query locally testable codes over the reals, right?
3 query.
3 query. Yeah. So I mean, it came up at least once before, and even Amir and I had the paper on locally correctable codes over the reals with a connection to circuit complexity. So these things are not used in practice for error correction, but they come up in at least in mathematical or theoretical situations. And so the theorem is that over complex numbers, the dimension of a 2-query code with error alpha is 1 over alpha to the 9. So what does this mean? So it's basically an impossibility result. So for constant alpha, you want to correct a constant fraction of errors, then the message length is constant. So there's no infinite family of codes.
Do you have something with more than 2 queries?
No.
But then, no, I'm confused because you can. Oh, you can correct with 2 queries, but you can't test with 2 queries.
You can't, there's no locally correctable codes with 2 queries. There are locally decodable codes with 2 queries, which is my next thing. So this is a separation between locally correctable and locally decodable. Locally decodable is that instead of correcting the code word bits, you can correct only the message bits. So it's a weaker notion because you can always assume the message is the first n bits here. So it's a weaker notion, and this is the first place where you can actually get a separation. So the Hadamard code works as a locally decodable code. It works over the rails. As a locally correctable code, it doesn't, and it can't. So there aren't any.
One over alpha is type because of repetition.
What?
1 over alpha is possible by repetition.
Yeah, 1 over alpha is possible by repeating each coordinate alpha fraction at the time.
You make 2 queries.
Yeah. So we thought we knew everything about 2-query codes, and apparently we don't. So the big open questions in this field are for 3 queries and above, but even for 2 we can still kind of say something new. So okay, so how the proof is by reduction. It's not by reduction, but it's first you observe that it's very similar to this line point incidence as this alpha Sylvester-Gallai configurations. I don't have a lot of time, so I'll just. So each coordinate of the code is an inner product with some vector, right? It's only for linear codes, obviously. Now, if you can recover a coordinate from 2 other coordinates with some non-negligible probability, it means that this VI is in the span of the 2 coordinates. So basically means that the decoder has to be a linear decoder. It has to take 2 coordinates and take a linear combination of them.
And you don't rule out anything which is not linear.
Yeah, so for infinite fields, over the complex numbers, you can prove that the decoder has to be linear.
No, if the encoder is linear.
Yeah.
But you don't rule out.
Oh, if the encoder, you can, it's over the complex numbers, a nonlinear encoder is possible. Yeah,
Completely possible.
yeah, I guess it's possible.
So this is another open
ruling
question, another open problem.
Yeah.
After this. Linear
But
cannot.
just for the motivations I have, linear codes are the only interesting case. Okay, so.
So there's a good comment by superlargist.
Yeah.
But if you allow nonlinear, you can pack the entire message into a single symbol of the. And just repeat
if
it.
the message is integers.
Yeah, if you have any integers, just like them like.
Oh, yeah,
leave them in the.
Yeah, you can take a mapping from any.
So you can just repeat
It's an infinite space, so yeah, you can spec everything using
also
non-measurable function.
No, of course. But you have to stick yourself in some. Maybe a writing nice way.
Yeah, so it makes sense for infinite fields to talk about linear codes, even more than in finite fields. So basically, we have this structure of points in space, such that for every point and every subset of size alpha that we erase, kind of the subset of errors, there's a pair outside the subset which spans VI. So if these are the coordinates and we're interested in recovering VI, and for every small subset that we erase, there are going to be 2 vectors, V2 and V7, that span V1. So it's a definition. So I'm going to define this properly in a second, but notice that you can replace the word span on the same line with very easily. So just change basis and scale things so that if 3 points are in a plane, they're going to be on a line. So this gives rise to the following definition of an alpha LCC configuration, which basically says that for every point and every subset of size alpha, if you erase the subset, you're still going to have 2 points, other points that are on the line with. This seems very similar to the previous definition. And in fact, if there are no repetitions, if all the points are distinct, then these 2 things are the same, up to constants. So you replace alpha with 2 alpha. But the problem in this setting is that you can have repetitions. So the code can repeat the coordinate many times. And originally, we didn't think this is going to be a problem. When we came to write the paper, we found out that, that it is. And we had to work really hard to actually solve it. So I'll spare you the details. They're really ugly. I mean, you have to work. You have to use this, find this family of triples in a much more intense, computationally intense way. But you build the design, and you need to do this in steps. Kind of first you take the things with that have a few repetitions, and you build the design on them. Then you throw them away, and you continue. There's some work involved. But this question of repetitions, whether repetitions help in locally correctable code, is we don't know the answer. Maybe there should be some way to just take a code with repetitions and get a code without repetitions with the same parameters. But we don't know if this is true. And okay, so I'll conclude very quickly with a couple of open problems. Okay, so how about a high-dimensional Sylvester-Gallai theorem? So there are theorems like Sylvester-Gallai when you replace lines with planes. So if you have points that span dimension 2k, they're going to be a k-dimensional subspace that intersect the set in exactly k plus 1 points. So it's a straightforward generalization. The proof is very, very complicated, this theorem. It was proved in the 60s by a Swedish school teacher, which I guess the only one that had enough free time to actually think about this hard enough. And later there are other proofs, but and we would be very happy to prove a high-dimensional analog of our theorem when you have this robust condition. This might be a step towards arguing about locally correctable codes with more queries, again over the complex numbers. So this is kind of an intermediate question. It's not a locally correctable thing, but it's very close. So hopefully, if you can do this, you can get something for locally correctable codes with some extra work. Another question that Dana brought up is what is exactly the connection between locally correctable codes and design matrices? So all the locally correctable codes we know come from low-rank design matrices. So you take a matrix that's a design, it has low rank, and that's basically, this matrix tells you what are the queries that you're going to ask. If you want to
low is not necessarily very low, right?
What?
Low is not necessarily very low, at least over finite fields.
Low means, n minus something that goes to infinity. Yeah, but low, I mean, not n minus a constant. Something not trivial. But all the constructions come from, so the structure of the query is a design. So if you have two coordinates in the code, if you take kind of a random word in the dual, the probability of hitting both is small. So the intersections are small. And the question is, so we show that basically these constructions, like Reed-Miller codes, for example, they don't generalize to the complex numbers. So if you ever think about a problem where you want to have something like Reed-Miller codes over the complex numbers, then you're out of luck because there aren't any. And the interesting question is to show that every locally correctable code basically has to come from a design. And it's not very I mean, it's tricky because you can kind of build contrived examples that are not a design, but then you can extract a design from them by, let's say, merging some coordinates and throwing away some and so on. But this is a very interesting question. If you can, if the answer is, if this is true, then you basically get a lower bound for higher queries.
The locally correctable codes over complexes, or
well,
are you
no.
asking?
So we don't have constructions over complex numbers at all.
Of course. Right.
What?
This is for just two.
No. For any number of queries.
Over any field.
What do you mean? The question?
No, the question.
Yeah. The answer might be different, but the question is interesting. It's more interesting for complex numbers because then you could plug it in with our results and get lower bounds. But it's just interesting anywhere. And so if this is true, then combining, if it's true and the design that you get is good enough, then you get lower bounds for more than two queries, which is it's a serious barrier. So it's something people thought about for many years, and nobody has any idea how to approach. And also, if you can get these low bounds, sufficiently strong low bounds, then you will get new families of rigid matrices. So I didn't talk about matrix rigidity. It's another question about support versus rank, and it comes in, it's related to circuit complexity, circuit low bounds. So you know, if there's enough progress in this line of work, then it might give us new rigid matrices, at least for complex numbers. For finite fields, it's probably not going to work, but I guess you'll hear about it at some point. Thank you. This is a Sylvester. Questions?
You promised a trick. Moving.
Yes, you want to let people go first, or?
Any other questions? Okay, so why don't we thank Zev and then we'll stick around.
Okay.